It's visible.
Yeah, it's coming up.
Is it visible now?
Yeah, it is. It is.
Okay. Yeah. What were you asking?
So there is I mean, we define the Lagrangian dual function, which
Uh-huh.
is a function of lambda and theta for a given x, something like that, right? And then we try to take the infimum of that, and then it is a concave. I
Hmm.
mean, that kind of thing, right? So I'm not able to exactly visualize that geometrically. What does that significance of that? Maybe, maybe the example will be good, or I don't know. Even general concept is also fine if you can.
So you're saying that proof part you didn't get.
Oh, yeah, let me just open the notes which are only for that.
Thinking aloud.
Oh, these notes which are shared, right? I mean, uploaded notes in that lecture 18 week 9. So the first two slides, first two what are the notes pages. Yes, yes, yes.
Okay. Okay. Uh, First two page, I think the same thing is repeated twice, no?
Yeah. Right. It seems
So I'll just take a screenshot of that.
uh, let's say this one.
This
Oh yeah,
particular.
it is actually same page. Yeah. It was same page.
So in this, so this set was defined, which consists. The set is defined in this manner, and you define the dual using. Like you can define the, in some sense, the optimal value of the primal using the set, and the dual also using this set. That part you understood?
Yeah, I think this I have understood. Yeah, and then correct, and then after that, that line is written, no, infimum of L x lambda theta, which is a Lagrangian over x.
Yes, yes. This part.
How it is connected? How that was connected? That I could. Oh, because it is coming from the above line, I guess. Oh.
No, so this is the optimal value. This is different. The optimal value of P is via this because the 0, 0 t, if you substitute here, then the minimum t that you can get, that is the minimum value of f of x. That is the optimal value of your primal, right?
Correct. Yeah, because that is correct. Because of 0, 0, it is a completely feasible, perfectly feasible set. Yeah,
Yes.
right.
And the dual is defined in this manner. It is the infimum of the Lagrangian.
Theta 1 and UVT, so that the multiplication becomes exactly like a so this actually it becomes a Lagrangian. Yeah. So d lambda t is a infinium of a function which is a Lagrangian function, defined over UVT belongs to G for lambda greater than 0. So it becomes the infimum of lambda x lambda theta over x. Yeah, makes sense. This also makes sense. Okay, so d lambda theta is a dual function, right?
Yes, yes.
Now, uh, uh, now since this dual function is a concave,
Yeah.
if the fx is a convex
No,
and
no.
jx and hx is also convex, or it is not required that to be holding true in general, it will be, or it will be only into that.
In general, it will be concave.
Okay, okay.
So we can prove that actually. Uh, so for some function to be concave, like f of x is concave means you can have some f of like alpha x plus 1 minus alpha y. This will be greater than equal to alpha times f of x plus 1 minus alpha times f of y, right?
Yeah, right, right,
And so if this is concave, then that means it should satisfy something like this.
right, right.
So that we can kind of check. So that means let's say I drop one of the value. I have some d alpha lambda 1 plus 1 minus alpha. Here alpha is between 0 1. So d alpha lambda 1
Yeah,
plus 1 minus alpha lambda 2. This is equal to infimum x Lagrangian. Uh, sorry, let's
x
take
lambda 1,
alpha also, right? Alpha lambda 1 plus 1 minus. Okay, no, I should write it as
0 also. But,
alpha lambda 1 plus 1 minus alpha lambda 2, correct?
yeah, because yeah, I substituted that number with this number. Yeah. So, infimum of a Lagrangians will require the x part, which has been already covered. So, okay, yeah, x and oh, sorry, yeah, lambda has been written with other. I mean, uh, effective lambda. Yeah,
Now
right.
we can look at these two, how they will be. So uh, the other thing that I'll have is alpha times d lambda 1 plus 1 minus alpha d lambda 2, right? This will be equal to infimum.
Lambda infimum of
Yeah, one more thing is, let me just keep this aside. So this Lagrangian is linear in lambda 1 and lambda 2.
right.
So that means we can write this as infimum x uh,
Uh, L
alpha
of x.
alpha times lx lambda 1 plus 1 minus alpha times L of x lambda 2. Is this clear?
So, because Lagrangian was the lambda was I mean that the second parameter uh, is a linear combination of lambda one and lambda two. So we could split that up. That is a hypothesis.
L is linear in lambda 1.
Yes, yes,
So L is linear in lambda 1 means if I write Lx comma alpha lambda, this is equal to alpha times Lx comma lambda.
right.
And L is linear also means if I write lambda 1
Some
plus lambda 2, this will be equal to this plus lambda 2.
Right, right.
This is the by definition of linearity.
Yeah,
So, and it is linear because it is defined in that way, right? It is the linear combination of these.
yeah, yeah, makes
So,
sense.
we get we can write this as this, and
Then we can subtract.
for this also, if we look, what we will get is we have alpha times f
Uh,
of x ls.
Lagrangian of x lambda 1 plus 1 minus alpha infimum of x lambda 2.
Yeah.
Okay, okay.
So now you have to look at this infimum property. So if I have infimum of x, some f1x plus f2x, and this will be greater than equal to infimum of x f1x plus infimum of x f2x.
Okay, yeah.
So by this property, what this will, like, this will be greater than equal to.
That will be always true. Yeah,
So that is what we wanted to prove. Like, that is the
yeah,
property of concave.
yeah. That's what it is. Okay, okay. Yeah,
And I think you are asking about this part also, right?
yeah, yeah. Mm,
So yeah, so here what is being said is this G, the G set in U, V, and T.
yeah.
So you will get like it will be some set in the U, V, T space. I think here only U and T is drawn.
Yeah. We have taken it out. That is fair. I mean that. That's simple.
So here uh, this P star will be some point, and if you draw the tangent,
Oh.
the supporting hyperplane at this 0, 0 P star point,
Hmm.
then the intercept at which this intersects T, this hyperplane.
Hmm.
So that intercept, the maximum intercept, is the optimal value of the dual problem,
Hmm.
and that gap what you have is the duality gap.
So basically, we are trying to draw this plane when u is equal to 0, right? Because of when that what supporting hyperplane at 0, 0 p star, right? So it has to be 0 only. So that means that there is only a, I mean, on that axis, right, of a t axis where there is intercept of a set g, that would be the only optimal type of thing. Is that what we are trying to say? Because p star would lie. P star would lie on that. I mean, P star would be a u equal to 0 and g set whatever value, right? It should be P star, no? Or maybe sense. This part, right? That green line which has been drawn.
Oh, sorry, sorry. No, you don't draw hyperplane at P star. You draw a hyperplane at the maximum. So you have to draw a hyperplane such that
Huh.
you get maximum intercept. So
Okay.
at P star you will get a fixed intercept.
Exactly. Exactly. So that's.
So you have
confusion.
to draw a hyperplane where you get the maximum intercept.
Okay, okay.
So I think here the diagram is sort of maybe
But
misleading.
that is true, right? I mean, if a maximum intercept will happen, see, if I draw from any other point, right, I am going to hit to this y-axis below p star only, and only if I draw a tangent, which is exactly at a p star, I mean that exactly vertical point, that's the maximum number which I would see. Is that fair?
So it will be like if you have some function like this,
Huh.
then the maximum intercept may be like maybe like at some point, let's say here, it
Huh.
becomes like sort of touching to this. So this is the maximum uh, intercept hyperplane that you can draw.
At that point, no, but intercept is like a intercept. What we are defining is a y-axis coordinate, right? I mean on t-axis, right, where it is hitting.
Yeah, yeah.
So it will be hitting in this example. It is hitting below zero in some sense, right? So if you look at a maximum, we are looking at a maximum positive number, no?
So you
So
want it relative to the p star value.
related to the p star value, right? Yeah,
Yeah.
exactly.
So related to the p star, the maximum gap that you can get.
Yeah. Oh, okay, okay.
So with P star you draw a hyperplane, and you that hyperplane is, let's say, something
Yeah,
like
exactly
this,
like that type of things, right? So yeah.
and the maximum gap that you get by drawing another hyperplane, that is
Hmm.
the dual value.
Okay, okay.
So the dual value will maybe somewhere here. So this gap is the dual gap.
Yeah.
If the maximum hyperplane happens to be at the same point, then it means the gap is zero between
Hmm.
the dual and primal.
Right, right, right. Maximum intercept of any supporting equivalent to this, right? And non-vertical makes sense because it should not be a parallel completely where it is not even hitting the
Yeah,
inter.
correct.
So G shade should not. Okay, okay, fine. I mean, G set can have a. I mean, this function, right? G can be a completely vertically up function, but that is not possible. That's what we are trying to say, right?
Yeah,
By not
something
having
like
a
this if it holds and
exactly like a complete vertical line, that is not possible, right? That's what we are trying to say, I guess.
I think that is not possible because D is concave.
D is a concave, right? Right. Hmm. Yeah, makes sense. Makes sense.
Or it may mean like dual is infeasible or something, and primal is infeasible. There may not be such P star.
Because gap will be infinite, and gap infinite means it is one feasible
Yeah.
one bounded something like that, right? So that may be the interpretation. Makes sense.
Any other doubt?
Yeah, just a second. So Slater point, it would, I mean, a slightly different topic. Slater point, right?
Hmm.
So if a feasible space is not a singleton,
Hmm.
will the Slater point always exist, or there is some other condition which will be required for a Slater point not to exist? Because Slater point, right? I mean, we saw that gx less than zero. we said j is equal to 0. No, I mean less than 0. I mean less than rather than equal to 0, we could do that. So we went with the feasible space. Is there any other condition which was required to mark a point as a straight line that I could not
You're
consider?
saying
Yeah, for a typical convex optimization problem,
mhm.
if if there are more than one feasible points, then there is always one Slater point. I mean that I don't know if that statement is
Not necessary, no,
true. Okay,
because it can be like
where
mm, just thinking.
so just open that. What is the definition of Slater point?
Yeah, I think you're saying if there is
So let's assume that there is no function. I mean, there is no concept like hx equal to 0, right? I mean, for simplicity. So there is no function minimize fx where subject to gix less than equal to 0, right? Now, if I find any point
huh.
which is less than 0, and that's why it is in a feasible space,
Mhm.
I can call it as a Slater point. Good. Except, no, I will just look at the definition, which was
I think definition was GIX hat is less than 0 and HIX hat.
no. So hix, I don't have.
Okay.
Suppose I don't have hx. I think that is in the other video. I guess. Other Slater point x star is a suppose x star is belonging to the S. S is a regular feasible space, right? Yeah. And suppose there exists x star such that for each either GX. Okay. So GX is less than 0 and GX is convex. So yeah, correct. So I'm assuming the convexity. So if I have a function which is which has got a so the function which has got less than 0 means it is a I mean it's not active state, right, type of thing. It is
Yeah,
that
yeah.
type of things. And uh, and if a function is convex, so a regular convex function having a sum in water internal or not water internal
Mhm.
point, right? If there is an internal point and a function is a convex, then it is always a constant qualification holds true, which means that it is a Slater point, right? I mean that in that case with the CQ2 definition. And if a point is on that boundary that is Jix less than 0, then Gix has to be affine. And if a function is affine, which means that I mean any two extreme values which I take, right, it is still in that state, right? I mean not equal to I mean alpha 1 minus alpha need not be 1. Or some need not be 1, right? So as I take any two values, it will still be affine, right? Yeah. So I think it should be true, right? If it is convex, then for a convex function internal thing, it's internal point, it is always Slater condition equals to.
Yeah, yeah,
Or
yeah.
Slater point equals to, right? Yeah.
Yeah, yeah.
Hmm. Right. Makes sense. You can experiment. Cool. Yeah, I have to still complete the assignment. I will probably try to do it sometime. Yeah. Thanks.
I think tomorrow is the last date, no?
Yeah. Tomorrow is last day, so hopefully I will get time till tomorrow. Thanks, bro. Can you just share with me again that link? Do you know that link where we have because what we upload are only the session thing, right? But not the link of a videos. of these things, right? You also have video, right, of what these problem solving sessions.
Yeah.
I remember to see in something like a one Excel sheet earlier, right, where it was mentioned, I guess.
Yes, yes, there is an Excel sheet. You want me to share the link to the Excel sheet?
Yeah, by any chance it's possible for you. Yeah.
Yes, I'm just opening that. Uh,
So I will have to go through last.
yeah, I pasted it in the chat.
Thanks.
So since last 2 weeks, 2 weeks back, I had some surgery because of which I couldn't take in class.
Oh, okay, okay.
So last 2 weeks, I think no students were joining. So I have just recorded it as it is. Some questions I have solved and I uploaded.
Oh, okay, okay. Sorry, I always wanted to join, but unfortunately I could not join. Thanks. These are very helpful. So you will continue for some more time, or?
Yeah, maybe I'll just discuss some questions
Okay, okay.
so that there is some content in the video.
Yeah, yeah, right, right, right.
Uh, so if you don't have any doubts, then I can discuss this question.
Yeah, yeah. I may have to drop off. I have a customer call like two, four,
Okay,
five.
no problem.
Sorry, I have to drop off, but thanks, man. These are helpful.
Okay, okay.
Thanks a lot.
So this first question that I'll discuss is this: you have some f of x and sublimation problem, and f is a two-dimensional has a two-dimensional domain, and you have one constraint g of x, and this is your feasible region, and they're asking they're saying that a constraint coefficient holds at x star if gx is active at x star and the tangent cone at x star with respect to the set S is as defined like this. The question is whether the constraint qualification holds at x star. That is the point given here 1 comma 0. So this, if you substitute 1 comma 0 in g of x 1 comma 0, what we get is 1 plus 0 minus 1 equal to 0. So it is an active constraint. Active constraint. So we can look at the gradient. The gradient of g of x, because we had the CQ1 condition that gi x star d is less than 0. assembly. Okay, this is the CQ1 condition. So we can maybe show this looking at the gradient. So the gradient is of the form x1 to x2. Okay, and at x star it is 2 0. So if we have some b d d1 d2, and if d1 is less than 0, then that implies transpose transpose d is less than 0. So there is this d. So that means this is like the constraint qualification holds at x star. So you can say this is true. Okay. So we use the CQ1 constraint qualification idea. So if d1 is negative, and if I take a dot product with this, then what I'll get is 2d1, and 2d1 is negative because d1 is negative. Okay. So that was the first question. And go to the second question. Okay, so here the CQ1 is again redefined, and we are given this problem, and we are asked if CQ1 holds at x star. So most probably this is an active point. If you look at g6 comma minus 2, you have this is equal to 0. So it's an active constraint. And I can look at the gradient, which is 1 comma 3. And I can define some direction. If I have d is d1 d2 and say d1 less than 0 and d2 less than 0, then this transpose d will also be less than 0. So there exists a D which satisfies this. So you can say CQ1 holds set external. So this is also true. So let's look at the third question. Which of the following are Slater points for the defined optimization problem? Yeah, so sometime back in the initial discussion we discussed about Slater points. So we need to check where the which points strictly satisfy these inequalities. So let's call this G1 and G2. So if I do G1 0 comma 0, then I get 0 which is less than 7. If I do G2 0 comma 0, then that is 0 which is strictly less than 5. So this is a Slater point. This is A, and can be at G1 1 comma 0, and that is equal to 2 which is less than 7, G2 1 comma 0, 1 less than 5. So this is also Slater point. If I look at C, G1 0 comma 1, 1 less than 7, and G2 0 comma 1, 3 less than 5. So this is also a Slater point. And if I have D G1 1 comma 1, that is 3, and G2 1 comma 1, 4 less than 5. This is also a Slater point. So all the options are Slater point. Let's say I add one more point E, which is 2 comma 1. So G1 2 comma 1 is equal to 5 which is less than 7, but G2 2 comma 1 is 2 plus 3 is equal to 5, which is equal to 5. So this is not a this implies 2 comma 1 is not a Slater point. Okay, for this optimization problem. So this is not. To all the original options they were Slater points. Okay. Let's look at this question. How how many variables are in the dual function of the optimization problem. So let's try to look at the dual. Dual is d lambda theta is infimum x, the Lagrangian, okay, for some optimization of this form gix less than 0 I equal to 1 to m hix equal to 0 1 to p, and the Lagrangian is defined as f of x plus lambda summation lambda I equal to 1 to n gi of x 1 to p theta I hi of x. So here what do we have? We have f of x, which is this, and we have one constraint, some g1 of x. So we will only have one variable in the Lagrangian, that is our f of x plus lambda 1 g1 of x. And the dual will be infimum of lx comma lambda 1. So we have only one variable in the dual. Okay. Corresponding to the one constraint. Okay, now we have this question. And we have this optimization problem, and then we have the dual function, and they are asking, suppose we are told d3 is equal to 10, d5 is equal to 20, which of this is valid value of d of 4? Okay, okay, so we don't have any information about what kind of function f and g are. We only know the value of the dual at 2 points. But one thing we know is that the dual is concave. Dual is concave means d, we can discuss the property of concavity in the beginning. Second, reacting slightly slowly to turn off some of the apps. Okay, now it's better. So yeah, minus alpha y, because this is concave, so we can do something like this: alpha dx. Okay, I should not use x, I will use lambda 1 lambda 2 lambda 1 1 minus alpha d lambda 2, where alpha is between 0 1. Okay, this is the concave property. So I can consider lambda 1 equal to 3, lambda 2 equal to 5, and alpha equal to 1 by 2. Then what I get is d of 4 is greater than equal to 1 by 2 times d of 3 plus 1 by 2 times d of 5. So d of 4 is greater than equal to 10 by 2 plus 20 by 2, which is 5 plus 10 equal to 15. So there is only one value which is greater than equal to 15, and that is 16. So we can say 16 is a valid value of d of 4. Others are invalid. Okay. So maybe if we have more idea about f and g, then maybe this may also become invalid. But given this information and using the concavity, 16 others are invalid. Others will not be there surely, no matter what f and g we take. Okay. Look at this question. We are given this optimization problem, and again d lambda is the dual function and x star is the optimal solution. Then there exists lambda such that d lambda is greater than f of x star. Okay. So what we are saying is the dual, there exists some value, there exists some lambda. It is only one constraint, so it is an R. There exists lambda such that the dual value is greater than the optimal value. Okay, is this possible? So by definition, the dual uh, lower bounds the primal optimal. Okay, how is that? Because dual is the infimum x, right? So d lambda is less than x lambda for all x. That means this is less than x star also, the optimal value. And we know Lx star lambda, this is equal to, one sec. This is equal to f of x star plus lambda times, so they are asking there is lambda greater than 0. G of x star. Okay, now here lambda is greater than 0, greater than equal to 0, and because this is optimal, gx star is less than equal to 0. Okay, so that means this is negative. Lambda gx star is less than equal to 0. So what can we say about the Lagrangian? If I remove this, this should be less than equal to f of x star, right? Because when I add a negative value, it becomes equal to the Lagrangian. Okay, and if we know this d lambda is less than equal to this, so that means d lambda is less than equal to f of x star. Okay, so that means this statement is false. The Fenchel dual of a function f is defined as, just a sec. The Fenchel dual of a function f is defined as f star y. So okay, this is the Fenchel dual. For f. Now we are given some f of this form, and we are asked the value of the Fenchel dual at some y equal to 5. So f star y is equal to sup of y transpose x minus 2x square. This is the Fenchel dual. So at phi it will be sup phi x minus 2x square. Oh sorry. Here it is x. Okay, this definition is incorrect. Here it should be x sup x. So it is phi x minus 2x square. Yeah, now it makes sense. Okay, because this is a function in y, so we take the sup x here. So basically we want the maximum value of this quadratic. Okay, so this will be some down facing quadratic. It max at somewhere here. So okay, let's say this is h of x equal to fx minus 2x square, and I do the derivative of h with respect to x at phi minus 2x and make it equal to 0. So x is equal to 5 by 2 equal to 2.5. Okay, so for this quadratic at maxima you will have the derivative 0. So I substitute 2.5. Find 5 minus 2 into 2.5. Oh sorry, this should have been 4. Derivative is 2 times 2x. This is 5 by 4. 5 by 4 is 1.25. 5 to 1.25 minus 2 into 1.25 square. So 25 by 4. Okay. Yeah, so this is the answer, 3.125. This was the Fenchel dual. I think this was just introduced, the Fenchel dual. And one property was that the Fenchel dual is always convex. Okay, and it is linear in y in some sense. The inner term. Fenchel dual is always convex. F star is always convex. Check it. The next question. Hmm. We are given this optimization problem. Yes, we are told that P star is the optimal value of the primal. If D star is the optimal value of dual, then P star equal to D star. So what was an easy way that was taught to us was, if you have a convex optimization problem and Slater's condition holds, then the primal is equal to the dual. Primal optimal is equal to the dual optimal. So this is convex. This is also convex. And we have one equality constraint. So we just need to check whether there is an optimal, whether there is a solution to this. Okay. So we can see it is full row rank. We can't get another row by a linear combination of the other row, because there is 0 and 7, 0, 5. Okay. So there exists X that satisfies Ax equal to B. Therefore, Slater's condition. So that implies that P star is equal to D star. So this is true. Okay, so the problem is convex and Slater's condition holds, so P star is equal to D star. Okay, I think that is all the questions. Maybe I can discuss one more question. See, you have image e power minus x sums into x square by y square less than equal to 0. question is, okay, they are asking what is T star minus T star. Thus later condition hold. Okay, this is the question. So this is equal minus x. So this is a convex objective, but is the constraint convex? So we don't know if the constraint is convex. So into, if you look at the gradient, let's say it is g of x, g of x from y, it is 2x by y square minus 2x square by y cube, and the Hessian, that will be okay. This is the Hessian. So if I look at 2y square so we may not be able to write this as a quadratic. So we don't know whether this is convex. Okay. But what we can see is x square by y square is less than equal to 0 implies that x square is equal to 0. So that means e power minus 0 is equal to 1. So p star is equal to 1. We can look at the dual. To increase the page size. So the dual, let's look at the Lagrangian first. e power minus x plus lambda x square by y square. The dual is inf xy. And we know x is equal to 0. X is equal to 0 automatically implies that this is 0. This term is 0. Okay, x is equal to 0 is when I put there, but here what can we say? We want the infimum. So I can have x, because I don't have here the constraint x square y square greater than equal to 0, less than equal to 0. Okay, but implicitly I have that y is greater than 0. Okay, y also need not be greater than equal to 0. Y just can't be equal to 0. So if I make x equal to infinity, and e of minus x goes to 0, but I can keep something like x is equal to y and x is very big. So e power minus infinity will go to 0. This will be equal to some lambda, I guess. But will it be equal to 1? That is what we need to check, whether p star is equal to d star or not. So let me take the case when lambda is greater than equal to 0. Then is the infimum lambda. But we can have this y to be something greater than x. That can make this equal to 0. Okay, so I can substitute y equal to uh, e power x, then x squared by e power x limit x tends to infinity is equal to 0. Okay, so this value, if you see, this is always greater than equal to 0 for lambda greater than equal to 0. If lambda is less than 0, then this can be minus infinity. So my dual d star is max lambda greater than equal to 0 d lambda, which is max of 0, which implies d star is equal to 0. So p star minus d star is equal to 1. So in that way also the latest condition is not satisfied. Okay. So this duality is quite often used in when you develop algorithms to solve optimization problems. And basically creating algorithms. Okay. So that's it for today.